Hey everyone, today we're going to talk about basics of density functional theory or DFT. So here for the overview we have an introduction, description of many electron system, and that will be followed by theorems of DFT, namely the Hohenberg-Kohn theorem and the Kohn-Sham theorem. So what exactly is DFT? You can read this one. Quantum mechanical atomistic simulation method to compute a wide variety of properties of almost any kind of atomic system, be it molecules, crystals, and so we can have the topological materials. So start with consider the n interacting electrons. So we consider that we have considerations such as the kinetic energy here, this one, the electrostatic or the Coulombic interactions, and of course the potential due to the interaction between the electron and the nucleus. So if we consider those, we will have a description of the many electrode system given by this Hamiltonian T plus B plus U operating the Schrödinger equation. So we just put those quantities here and operate it on the side, then we'll have the energy. But this has been proven to be quite difficult to solve, and also that would also mean that using it in computations would be computationally expensive. So we have to find another way, and that is by describing the system with electron density. We have here our electron density can be described as n times this integral, the probability function, and this is interaction between atoms, electrons I mean, and so we can also extract from this one that the Schrödinger equation for the ground state would be a unique functional of the electron density. And for any observable O, have its expectation value as this one. So, of course, that would also mean that the observable is unique functional of the ground state electron density. Hence, we have our Hohenberg-Kohn theorem, the ground state properties of a quantum mechanical system, which I have said the O is uniquely determined by the ground state electron density. So, if we have the observable E, we can also write it as this one, a unique functional of electron density. And we have here the Hamiltonian operator. So, we'll focus first on the contribution of B, which is now a function of electron density, the ground state electron density. And let's focus on the potential term. We'll call it V sub S. And then the first one is the external Coulomb force of the nuclei. Second one will be the Hartree static repulsions. And of course, the quantum mechanical effects in the form of exchange and correlation. So the exchange is just due to the quantum spin. So have to restrict that the spin must be conserved. Correlation, because an electron should be affected by the motion of the other electrons. And we call this tissue system as the Kohn-Sham system of non-interacting particles with potential Vs. So we move from interacting particles to non-interacting particles with potential V sub S. So that would mean that each electron would be experiencing the same, more or less the same potential. So here, let me read the non-interacting particles, typically the electrons that generate the same density. as any given system of interacting particles. We have here our projector. So, so much for that one. We have our quantum theorem. The electron density that minimizes the energy of the overall functional is the true electron density, corresponding to the full solution of the Schrödinger equation. So with those two, we have our DFT. Here we have our quantum equations. So we have 1/2 Laplacian V R V H V X C, which is just the Vs operated to the wave function, then it should yield the minimized energy. But we have here the cyclic dependence. So these two potentials, and of course they depend on the electron density. The Schrödinger equation depends. I mean, these potentials are needed so that we can find the electron density, and then the Schrödinger equation must be this functional of the ground state electron energy. So we need to find this first, but of course to find the potential we need to find the electron the Schrödinger equation describing the system. So it's quite cyclic. So what we should do here now is to have this self-consistent field calculation, or the SCF calculation. So we have to initially guess the electron density, and then from that we can obtain the fictitious potential V sub S. This is just the V sub S, and of course you can have now the operator and have this one, and then it should yield the electron density, and this electron density will be checked if it is the same as the initial. So that would mean that it is consistent, and if it is not, then we have to try another guess. So we have algorithms for that. But in DFT there are also types of pseudo potential, or the potentials that are what you call this, pseudo. Okay, yeah, pseudo. They are not the real potentials, they are just estimates, but they are, I think, the RRKJ pseudization. They The way they pseudize the potential yields an estimate of the electron density. So you can, those are quite they already give you a hint of what should be the electron density of the system. So there are those types, but there are also types of pseudo potential where there are no such things. So you have to have an educated guess on what would be the initial electron density. Then if it is consistent, usually the difference is around 1 times 10 to the minus 6, or minus to minus 8. I mean the order of negative 6 times 10 to the negative 6, or times 10 to the negative 8. Then it is said to be self-consistent enough, and could be a good approximation of the system. And from there, we have, since we have these three, this one, and this one, then we can have and can extract the information from the system: energy, forces, eigenvalues, and then we can use those in our non-self-consistent field calculation. Since we already know these three, we don't have to use the self-consistent field calculation, and we can just obtain the bond structure, etc. So then for the next one, we will have an example on the using DFT under quantum espresso. So that will be all. Thank you.